There's some problems with Teams, maybe, I don't know. Okay. I hope my screen is visible. What I'll try to do is do today is we'll try to finish off what is the TD0 algorithm. You can hear me, right, all of you?
Yes.
Yes.
Okay. So we'll try to finish off TD0 algorithm with linear function approximation in the on policy setting. This is when, and we'll finish off all the theory part of it mostly today. And and then we'll see how we go about the next topics, more advanced topics as we go forward in the last few weeks of the course. So what I'll do today is, and I'll after it will be a shorter class because I'll finish off the proof that I had started off last time, and then we'll see the. I think some of you had a problem with the first assignment. If you can show that as well, we'll have a look at the code and things like that. Okay. So let's get started. So if you recall, there are a few things. See on the left of the screen. Uh, if you see on the left of the screen, I have written down the entire TD0 algorithm from start to the end. What are the few things that I've written down? So I have written down. Okay, one moment. Yeah. So pi was the policy. So all of you recall the main thing of reinforcement learning is the policy function that we choose. That is, at a given state S, what is the action we select, right? Action is selected based on the policy, right? So this is the first thing. Then the second thing we saw was the value function. That is, what is the definition of the value function? Do you recall? Value function based on the policy pi. The entire reinforcement learning is built on this.
Expected long-term reward for a state.
Okay, for starting state. So we wrote down from I equal to 0 to infinity, gamma to the power I, reward of Si, Ai, Si plus 1, given is 0 is equal to S. Yes or no? This is what we said. Then we did the tabular methods and so on, and we went to linear function approximation, where we said that we had a matrix of features, right? For every state S, we had a phi of S in how many dimensional space? RD dimensional space, right?
RD, yeah.
Yeah. So these were features, like we saw angular velocity and then momentum, and then we had velocity acceleration and so on for a cycle to balance. Then we had other constructs such as the three-stage reward function. That is, starting from a state S, if you take an action A and you go to ST plus 1, what is the reward that you expect? ST, AT, ST plus 1. This is the expected reward. Okay. And the last thing was, when we tried to do linear function approximation, we did V pi is equal to phi of W. What does this mean? It means that we took, again, people who have not attended the classes, this is a very, very simple thing. So this is V pi of S is, can you tell me
We
what
assume
is
that
it?
it is in the column space of feature vectors.
Correct. So we do something like this. We say that, so V pi of S is for all the features from 1 to D. So this is what we said our value function would be. Correct? And we learned these. Yes or no? Okay. Any questions? So for every state, we ended up learning this. So this is basically nothing but phi of S transpose W. Correct? And then we went to linear function approximation. What did we say? How were we learning the function? How were we learning W? You remember? We said that we will learn a D norm. We will minimize the D norm. What is the D norm? Do you remember? We know L2 norm, right? X transpose X is L2 norm. What is induced norm by a diagonal matrix D? Do you remember? This is V pi minus phi W transpose V
Into
pi.
D.
Good. So this is normally L2 norm, right? V pi minus phi W, the length vector. Correct?
Yeah.
The square of that, the square has not yet appeared.
And that's
Yeah.
a matrix norm, right? Yeah.
Yeah. So this is a vector norm induced by a matrix, not a matrix norm. Because all we are doing is multiplying each of the term with a D. So this becomes D. Okay. So this is what? This is nothing, basically this is Vi. So this is D pi of I, V pi of S minus phi transpose S W. That's all we did, right? 1 to S. Correct. Normally this term would be 1 in a vector norm, in a normal L2 norm, right? Length norm, Euclidean distance. Correct. And here we are just weighing the terms by their relative importance. What is D pi? Do you remember? Why did we do D pi?
Yeah, weights of each feature, I
Wow,
think.
correct.
It's
But what is it? It is the stationary distribution of D pi was the stationary distribution, right? Of the transition matrix. If you have, this will help you recall the entire algorithm. Okay, this is the transition matrix. We have done this multiple times, that when you traverse a Markov chain, so basically D pi of S dash is the probability. What is it? Do you remember? Probability of being in a state S dash. Do you agree? This is the probability of being in a state S dash. So can you tell me, well, how can we write this in terms of the transition matrix? I'm doing it once again so that you remember. This is basically
D pi dash into the sth column of the transition matrix, right?
why this is basically ST plus 1 is equal
Yeah,
to S
but
dash.
total probability theorem, I think we did it.
Correct. Yes. So ST plus 1 is equal to S dash. So I condition on ST equal to S and I multiply on probability ST equal to S. Correct. And then I sum over all S. Do you agree?
yes.
Law of total probability. So this is P pi of transition from S to S dash. And this is D pi of S. And you sum over all the S's. Correct. So what happens is, so we say that if D pi is stationary, the running the Markov chain does not, remember, change the distribution, right? We showed it last time that we could, this could have been 0, 1 and so on. This could be the distribution at time 1 if we had this as distribution at time 0. So, but we say that 0 are equal to the time at 0, D pi at 0 is equal to D pi at 1. If this is true, then this is called a stationary distribution, right? So what is happening is you are in the Markov chain from S to S dash and so on. So many states are there, 1, 2 and 3 and so on, and you may be traversing the Markov chain, and it is told that if you are going to a particular state, you have also done this in your assignment questions where you have written down the balance equation and so on. So if you go to a particular state, the probability of being in that state in the next state is also the same as the probability that you start from any state and you end up being in that state. So it's like all the states, all the probabilities coming into that state. That's the stationary distribution. idea. And then we said that we took the derivative of the, this was the loss. We took the derivative of the loss and we came up with the iterative TD0 algorithm, which said that it is the temporal difference term where we have the one stage reward, the value function at the next stage, v pi of st plus 1, and the value function of the current state, right? And then we had multiplied it, because it's the derivative, we multiplied it with the feature matrix. That we derived everything, all of this, right? And then in the last two sessions, what did I do? I told you what is the point at which this algorithm makes you converge, right? And we found out, do you remember? We found out that the optimality point of optimality was A inverse B, where A was phi transpose D, 1 minus identity matrix into 1 minus phi, right? So this is, first tell me what would be the dimension of A? Can anyone tell me? So we said that in the last two classes that this algorithm would converge to this point. Correct? So what is the dimensionality? What is it? Phi transposes dimensionality?
D cross D. Yeah.
D cross, correct, D cross D. So this is S cross S. This is again S cross S, and this is S cross D. So this is D cross D. Similarly, this is D cross S, S cross S, S cross 1. So this is B is again RD. So what is R over here? Do you remember? So D, I remember D. What was D? D is the diagonal matrix of the probabilities, right? Of the. So D is capital D. What is capital D? Do you remember? Diag of D pi. Yes or no? All the probabilities that we have for the invariant distribution, the stationary distribution, we put it in a diagonal matrix. Correct? That is D. Phi is the feature matrix. P is the transition matrix, and R of S is the one stage reward, right? Correct? Any questions? So this is what we did last two times. So if you have this big picture in your mind, so I will write these two things down. So TD0 with the linear function approximation. Approximation. What is the, so if you're following, what is W star? Can you tell me? W star is?
The final optimal value of.
Correct. A inverse B, which is? Let us write it down. Phi D I minus gamma P pi phi transpose. Is it correct? Inverse pi dr. Is this right? Phi transpose is in the beginning, phi is at the end. Is this fine? This is A. This is B. Do you agree? Questions? And do you recall what was the original objective of the TD0 algorithm? V pi minus phi of W. Correct? This was your W, say W hash, argmin of W. Do you agree? This was your original objective. Any questions? So if this was your original objective, what is W hash? We already know that, we have derived it. We took the derivative and set it to 0. Then W hash was phi transpose d phi inverse phi d v pi. Yes or no? I wrote it down here as well. V pi. So correct. So how did we find this out? Do you remember? Do you want me to do this again? I missed transposes here. You're not telling me. Am I audible? Hello? There's something you want to ask? Okay, so this was obtained by taking the derivative v pi minus phi of w d squared and setting it to 0. So this was obtained, we obtained phi transpose d v pi minus phi of w equal to 0, and we said that this is equal to w star or w hash. The optimality point is phi transpose d phi inverse phi transpose d v pi. So this is what we derived in one of our previous classes, that the derivative of this equation is this, right? We derived it extensively. So now you see there are 2 points over here. One is w hash, which is the point we desire, right? This is the desired optimal, desired optima. And our algorithm is giving us this optima. So I want to know how far. So today's 2 points interesting question is first of all A invertible? We have inverted A, correct? The easy question, is A invertible? And the second question is how far is phi hash, that is the intended point of convergence, from the point of the convergence point of the TD0 algorithm with linear function approximation. Any questions? Can you hear me? I don't want to go ahead unless this is clear.
Yeah,
This is set
can
right.
you and it's clear.
Okay. So this was sessions 14 and 15, and this was session 13, 12 and 13. So we saw that this W hash and all was the point of convergence we wanted, but we ended up getting this W star. So now these 2 questions we'll try and answer. So let's do some +2 maths. So first question is A invertible? If if A is invertible, do you agree W star is? If A inverse exists, okay, so W star is unique. Do you agree? Because it's a linear function, product of two matrix and a vector, that will give you only one value. Do you agree? No problem. A inverse is unique, B is unique, so you get a unique solution, W star. Okay, so that's what we'll try and see. So if W star is unique, let's try to find that. So first, let's take a. So how did we obtain the A inverse B? We said we got this from here, right? So we said that we found out the ODE that the stochastic TD0 algorithm was tracing, and we saw that this was the ODE it was tracing, right? B minus AX. That was the derivative, correct? dx dt, that the first derivative of x with respect to time was B minus AX. That's all it was. So now tell me one thing. So we set this to 0 because this was a fixed point. At fixed point, the derivative has to be 0, yes or no? So we said that xt has to be A inverse B. This is where we obtained the solution from. So let us take an example and see when would A inverse exist or this solution exist. So let's take a 1D case where x dot t, say x is scalar, and so this is the derivative that I have. This is the ODE that I have, differential equation that I have. Can we solve this? Easy to solve, no problem. Can you help me solve it? So what I'm trying to do here is trying to see when the A inverse exists, when it exists. Let's try and see that. B minus AX is equal to dt. So if there is a question, you can ask me, stop me, because I'll think that this integral is easy for you all. So this is B minus AX 1 by A minus 1 by A. Correct? So I'm integrating. So I am telling you that x0 comma t0 is the initial point. I hope this is clear to everyone. and then I'm integrating to any arbitrary x and t. Fine, I'll get the solution to this differential equation, the ordinary differential equation. So log of b minus a. Yeah, question? T minus t naught minus a b minus ax is equal to b minus ax naught e to the power minus a t minus t naught xt is equal to b by a plus ax naught minus b by a e to the power minus a t minus t naught. Is this correct? Everyone agrees? This is the solution to the differential equation. So if this is clear, now tell me, when does a fixed point?
Sorry, could you just explain how, like we are deriving that A is invertible from this? I just missed out there.
I have not yet said A is invertible or not. I'm just saying, say we had this equation, right? We had this ODE for the TD0 algorithm, right?
Yeah,
This was the
yeah,
this is the ODE that we found out. We
yeah,
derived the ODE and found, and we told that A inverse B is a solution if A inverse exists, right?
yeah,
Because it has to, fixed point has to be zero, derivative has to be zero because there's no change there at the fixed point. Correct?
yeah.
So the fixed point is constant,
Okay,
therefore
got
the
it.
derivative.
Yeah, yeah, yeah.
Yeah. So now I am taking a 1D case because X and all these are 2D cases with multi-dimensional, high dimensional calculus. So I'm trying to find out what is the condition for it in a low dimensional space, like it's like a scalar case. Fine. That is okay, Shubham.
Yeah, fine. Yeah,
So now you're okay with me solving this ODE as well?
yeah, that's fine. That's fine.
Okay. So now you tell me, when does a fixed point, when will this fixed point exist? Tell me that. So if the fixed point has to exist, this has to go to zero, right? Because it's an exponential term and this is the constant term. So e to the power minus a t minus t naught must go to zero as t tends to infinity. Yes or no?
Yeah,
So a has to be greater than zero. Yes or no? If a is greater than zero, t naught is finite. So t goes to infinity, e to the power minus infinity is zero. Correct?
Yes.
Maybe I just put it more. Limit a tends to infinity. This is zero. So, but if see a is less than zero, what will happen? See, you will not have a fixed point. If a is less than zero, what will happen? Tell me.
that whole term will become infinite because e to the power something positive power.
Correct. So e to the power of minus a t minus t naught goes to infinity as t tends to infinity for a less than zero. But now everything depends on x naught. If it was still infinity, it was okay. But see, if x naught greater than b by a, right? Xt will go to infinity. Will go to infinity as t tends to infinity. Do you agree? Because this term is x naught minus b by a is greater than zero, the positive term. Correct? Now you tell me x naught is less than b by a, what will happen? Xt will go to minus infinity. Yes or no? Because this x minus b by a is negative. Yes or no?
Yeah,
And see, if x naught is equal to b by a, again you get a fixed point. Xt is equal to b by a. Correct?
yeah,
Fine.
got it.
So now you see there is no fixed point. As t tends to infinity, no fixed point exists. No fixed point. So that is what I want to convey. So this A being greater than 0 is critical for fixed point to exist. Okay, so in matrix form, what happens is for a fixed point to exist, this A greater than 0, I have taught this last time in linear algebra as well, is equivalent to saying A greater than 0, which is positive definite matrix. Okay, so A greater than 0 means a positive definite matrix. What does a positive definite matrix mean?
It
All
has five
eigen
conditions: eigenvalues 0, and determinants, leading determinants greater than 0, and then
correct. All
I forgot.
eigenvalues.
Yeah.
No, all eigenvalues are. This is enough. This is the sufficient condition, sufficient and necessary. All eigenvalues are greater than 0. Okay, so there are other conditions like symmetricity and so on. We really don't need those in our case because our matrix A is not symmetric. Do you see that? Our A matrix is not symmetric. You take a transpose of this, you will not get a symmetric matrix, right?
Yeah.
This is the A matrix. So there, that symmetric thing, whole symmetric thing will not hold at all. So there are in matrix algebra, we consider A to be symmetric if this is positive definite, but in this definition, we are not going to assume anything. So basically what happens is ax naught squared must be greater than 0 for a matrix to be sort of in 1D case, ax naught squared must be greater than 0. And in the ND case, what will this turn out to be for all x? So in the ND case, this can be positive definite matrix can be defined as any matrix where the quadratic never goes below 0
Yeah,
line.
yeah, yeah. This is the main definition, right? This one, the
Yes,
quadratic is. Yeah.
correct. So in our case also, we say that a quadratic is positive if this never goes 0 in a 1D case, right? Ax squared plus bx plus c, the determinant is less than 0 and
And
leading
that's
term is,
called the energy, right? That's the energy.
yeah,
The energy is positive. Yeah.
correct. So it's always this x transpose ax, whatever energy that you are saying, it's actually extracting how much energy that the matrix has, or its amount of the eigenvalues, the eigenvalues that it has. So it's like the leading eigenvalues and so on. So this quadratic must be greater than 0. So let us see how do we prove that this quadratic is greater than 0. So why is this quadratic greater than 0? You can go and see the videos last time. So let us try and see if we can really prove that this is greater than 0. So let's try and write down the definition of A first. What is the definition of A? A is, we'll just do some linear algebra today. So that completes a lot of things. So what is A? Phi transpose D I minus. I think if you note this down, it will become much easier for you to remember these terms. It's always not important. You can look up. At least during the session, we can write it from memory. Okay. So now A is not inverse. Sorry. This is A. Correct? So remember that normally A hash, whatever it was just phi transpose D phi. We have this extra term coming in over here, which is identity minus the probability matrix, transition matrix. So let's try and see what is this. Phi transpose D phi minus phi transpose D P phi phi. Correct? So now what do we have to do? Z transpose or X transpose X. Correct? This is what we have to see. Is greater than 0 or not? Help me write it down. What will this be? Phi X minus X transpose phi transpose dp pi phi. x. Okay. So now you see the first term that I have over here. How can I write this? Do you remember we have done this before once? This is, let us write phi x as some y. Okay, this will help us to simplify a lot of calculations. So this is y transpose dy minus phi of, or gamma of y transpose d p pi y. Okay, these are the two terms that I have. I can write this. This is okay with everyone.
Yeah.
Please stop me. This is really interesting algebra. So now you see, do you remember this term? What is this? What is y transpose y? Do you remember what is y transpose y? First of all, tell me what is the denorm of y?
Y transpose dy.
Y transpose dy, where D is a diagonal matrix.
Yes.
Okay, so we can also write this as this. This is one of the note equalities. I have done this before, but just for completeness, d to the power half y. This is d to the power half y transpose d to the power half y. This is d to the power half y 2 if d is greater than 0. That is dii greater than 0 for all I. Correct? We can take a square root for every term. No problem. Okay. So this is any d norm can be written by, just take the vector which norm you want to find, and taking that vector, you just multiply with the half of the diagonal matrix and you get the, just all you're doing is rescaling the vector. So if you have these vectors like this, these components of this vectors a, b, c, or y1, y2, yd, you are rescaling it as d1, d2, or root d1, root d2, root yd. And then, is the intuition clear? And then you take the L2 norm, right?
Yes.
Okay. Now, you see the first term I already know. What is the first term? ZD or YD squared. Yes or no? No problem. That's what I proved over here. By definition. Correct?
Yes. No issues with that.
But the second term is the problem. I have this p pi matrix coming in. What do I do with that? So let us try to write this down once and then see what this turns out to be. Okay. So let's write it down. So why did I write this way? Let us try and see. So d pi y, we'll try and do a little jugglery of these terms. So let us try and do that. So if this term is there with us, what can I write next? So let us take a norm of this. We'll take it, don't worry. So this term, can I write this as y transpose d to the power half p pi y? Can I write this? I can write this, right? I'm doing the
Yes.
same trick again. So now if I take a norm of this term, because it's a quadratic anyways, I'm taking the absolute value of the quadratic. What can I do? If I take the quadratic's absolute value, what relation can I use? Do you agree the quadratic has to be greater than the original value, the norm, of course, greater than or equal to, because you're taking the absolute value. If it was negative, it will turn out to be greater than negative, that is positive, right? If it was positive, it will
Yeah.
be equal.
Yeah.
So now what can I use? Can you tell me? We have done this a few times in the past. The Cauchy-Schwarz inequality. So whenever I have two vectors, I can write it down into two terms. See, d to the power half y is one vector, right? This is one vector. And this is one more vector. Yes or no? Do you agree?
Yes.
I'm taking the L2 norm. D to the power half p pi y. Okay. Now, again, I have derived one equation. That is equation 1. What is this equal to then? yd. Yes or no? The d norm, d to the power half into y from equation 1. Please help tell me what this equation will be. Can anyone tell me? Instead of the L2 norm, what can I write?
I can write the d norm of y.
D norm of y and
This is the um,
d norm of py.
yes.
Correct? So all I have to do is play with this term. That's all I need to do. And then I can try to compare with this. How is it different or same? So let's try and play with this term. It's p pi of y. So now you tell me this term p pi of y. Sorry, y. If I look into this term, the square of this term, what can I write? Can anyone tell me? This is p pi y transpose d p pi y. Yes or no? This is what I want to use, which is equal to, which is what is it equal to? See, d will come out, right? So it will be for all s, d pi of s, and then you have this inner term, correct? The square term, which will remain. I have told you whenever this is a d norm, you weigh the individual components and then write down the square of each component. Do you agree? So let me write down the step one at a time. So if you're not following, s, yes or no? Do you agree? I took a square as well. It's not visible yet. Yes, that's all it is. So whatever square, whatever the norm you want to find, you find it for every s and then multiply by d pi of s. That's all we are doing. Then what can I write the inner summation to be? We have already done this once. This is, what will I sum across? Across all s prime, yes or no? P is a matrix like this, right? For every state, you see S1, S2, dot, 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 SS, right? It's a S cross S matrix. And Y is again S cross 1 vector. Correct. Now tell me, how will I write this? P pi of, from a particular state S, P pi of particular state S. Where am I going to? See, it's the, yeah,
Yeah,
tell
we are
me.
just summing over all the states that it can go from S.
Correct. We are summing over, sum
S
over all
dash.
the states. Yes, sum over all states. It can go from S. That's all we are doing, because it's a linear combination y1, y2, dot, 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 ys. That's all we are doing. It's a linear combination of the columns. Okay, so this is, say, sum s dash y of s dash. Here the first multiplication, then the isth column. So s dash belongs to s, the whole square of this. So now, if you've understood this, the more important thing is, more than this, is trying to figure out one thing over here. So the important thing is, do you see does the inner summation resemble something? Do you see that? It's a, I will write it down for you and then you may be able to appreciate it.
Yeah, it's an expectation of y of S dash.
Yes. And then the square of the expectation, right?
Yes.
We have an square outside the expectation. Everyone else is following as well. Any questions?
Yes.
We should condition. That's one thing we should write.
Correct. So this is exactly, so I wrote it P S dash given this way. So you can also write it as
Because I didn't
S,
notice.
S is equal to S. Yeah. You can write either of these. No problem. Both are correct. You need not, if you write this, you need not write what the expectation is over. Okay, that's right. So now tell me, we can do one thing. So I will tell you, say there is something called as I taught it like 2 sessions
Yeah,
back.
Jensen's inequality.
Jensen's inequality. I have taught, you can go and look at the video of the proof of the Jensen's inequality. I'll share the link in the description. But basically, I'll give you the intuition of what Jensen's inequality is. So if you have a convex function, do you know what is the definition of a convex function? A definition of a convex function is a line joining the convex function is you take any 2 points. So do you agree the right hand side is just the midpoint theorem that we use in coordinate geometry in school? So it's a convex. So any point for any theta between 0 and 1, the midpoint or the what midpoint is when theta is half. The convex combination of these 2 points, x and y, or we can write x1 and x2 if you are thinking that y is the y-axis, x1 and x2, x1 and x2. The convex combination, that is theta and 1 minus theta, will lie above the curve. So any 2 points, if you join any 2 points on the curve, join any 2 points, it lies above the curve. It lies above the curve. Right? So if you take similarly, that is theta 1 minus theta 2, somewhere you see this is f of the convex combination, which is below, right? Yes or no? Do you see the intuition? No problem.
Yes.
Okay, so what does Jensen's inequality say? The Jensen's inequality says that if you have a convex function like this, okay, so I have a convex function, so I'll write down the Jensen's inequality, draw the Jensen's inequality rather here. You have 2 points, right? Say x1 and x2. The easy way to remember is, if I have just 2 points on this curve, right? What will be the expected value? Somewhere in between, yes or no? X1 plus x2 by 2. Correct? This is the expected value of x. If I have only 2 x's, correct? x1 and x2. And they are equiprobable,
Yeah.
whatever it is. It will be in between. Okay. So now you see the expected value is here. And this is some function of x. Let's see what happens. So now if I take the function and put the expected value in the function, rather than taking the expectation after using the function. See, there are 2 things over here. So if I use the function before, I get these 2 points. Yes or no? Do you agree? Fine? Yes or no? I get these 2 points. And then if I take an expectation, I will get, this is the expected value of f of x. Do you agree? In between, somewhere here. Yes or no? But
Yeah.
if you take, so this is, if you put the function on the expected value, you see it is below the expected value of the function itself. Yes or no? Right? First, if you take the expected value and put it through the function, it will be below or not. So we have Jensen's inequality says that
Yes.
You always remember this graph. This is the easiest way to remember. The proof is a bit involved. You can go and look at it. But the easiest way to remember is if you take an expected value, it will lie on the sum of the line that connects the function values at those 2 points. So this will always be above the function. So correct? No problem. Do you agree? X square is a example of a convex function because it's clearly visible. A unique cup-shaped function, U-shaped function will be a convex function. So I can use, so what is the function in this equation? The equation 2. It's x square, yes or no? Fine. So now what can I write this? Can you tell me? Using Jensen's inequality? I can write this as d pi of s. The expected value of f of x, tell me, what will it be? Ys prime I'm waiting for questions. See the expected value of the function by Lotus. I put the expected f. What is f of x? Here, it's x square, yes or no?
Yes, no issues.
Okay, there are no issues. Let us write this down. So this can be written as s belongs to s, d pi of s, summation of, again I'm going to write it down, I'll expand this, s dash given s, by s dash in s squared. Fine with everybody? So now you see this becomes very simple. I'll give you just a moment to tell me what this answer is. This is very easy. I'll just replace the summations and you will tell me what does this mean. What is this inner summation? We have done this multiple times. See, d pi is the stationary distribution, p is the transition matrix. Then we can use the stationarity equation, yes or no? This is exactly what I did, no? I'll just show you where I did it. See, this is exactly what I did. See, this is d pi of s dash, yes or no?
Yeah.
So this is basically d pi of s dash because we are doing is starting from a state. We are trying to go to a state s dash and we are summing over all the states it can come to. So if you are going to s dash, all the states sy, all the possible states it can come from by law of total probability. This becomes s dash in s, y of s dash, d pi of s dash. Now, does this ring a bell in some of you? This equation?
It's the d norm of s dash. Well,
Or y? S dash is going to be summed up over, right?
yeah.
Is the d norm of y squared. So it's squared again. So now you see, so I started from the square of py squared, p pi of y squared. So I get an equation. So I get an equation, very important, VVI important equation, which says that p pi of y
Less than the
d,
d norm of. Yeah.
correct. Very good. This is called non-expansive. This is what we proved. VVI equation. So anytime you multiply a probability matrix with a vector and then have the d norm of that with the transition matrix's d norm, the stationary distribution, you see that the length of the vector never, did I write it correctly? The length of the vector never increases, right? So the the left hand side here is after multiplication. So if your vector size was something like this, you multiply it with the probability matrix, the vector size is only going to decrease and not increase, right? That's what it says. Do you agree? Everyone, this is the intuition or the geometric. If you go to the column space of, so why does this happen? This is because you're projecting out on the column space, right? When you ended up projecting on any vector v, if you end up projecting on a column space, it will become shorter, yes or no? That's what it's trying to do. Okay, so we can replace this equation. So this is, say we write this as equation star from star. From star, we will write this as, so this term is, tell me what this is going to be. We have already derived this. This term is going to be, yes or no? Fine. So if this is greater, then if I put a negative sign, what will it be? Greater or lesser? Do you agree? This will be greater, x transpose ax. Because there's a negative sign, no? The inequality will flip. The larger, if you subtract a larger term, so this is larger. If you subtract a larger term, so you will get a smaller value, yes or no? Than the equality. Right? So
Yeah.
I'll get gamma d square. This will be equal to 1 minus gamma d squared, which is greater than 0. Do you agree? Clearly, because gamma is greater than 0, between 0 and 1. That is the discount factor. So we clearly see that, so therefore we see that A inverse exists. Therefore, hence, A inverse exists. The proof is below. QED. Okay, any questions? So now we have seen A inverse exists, therefore we have a unique fixed point. The last 3-4 small equations that we'll be proving is going to be how far is the fixed point from the optimal, right? So we have answered one of our questions today. Where is it? If A is invertible, yes, it is invertible and the solution exists. So now the second question we asked today is how far is y star, phi star, again it's not phi star, sorry, w star from this, right? W hash from w star, the point of convergence of the linear function approximation algorithm. You're not telling me these small typos. Phi is fixed. Okay, so now we will do something again. It is a reminder for all of you. W hash is the original solution to this equation, where we know that phi, the W hash is nothing but this. We have solved it before. I have written it down today as well. How far does it take from the point of convergence? So now tell me something. There's a clear inequality over here. So W star minus V pi and phi W hash minus V pi. Which of the following will be greater? Which is greater? By triviality, but there's no question regarding that. So
W star,
recall this will be
because
greater.
W dash was, yeah, W dash we defined as argument, so there's no
Very
point.
good. There's no debate here because this is defined as argument of any possible. Very good. This is defined as the argument, anything minimum. This is already the minimum possible. Minimum possible. Anything other than that will be greater. Will be greater. This is trivial. Okay. Because by definition, and that is trivial by definition. Very good. So now what I'll do is I will try to find out an upper bound. So as I was telling last day, Antariksh was asking me, so aren't they the same? I'll say they're not the same. We'll see why they're not the same. See y star minus v pi of d. See, this is a useless inequality. At least non-informative. We should not use this word. Non-informative inequality. Why is it non-informative? Can anyone tell me? What is the logic behind it being non-informative? So inequalities, you really need to think a little bit. Why is this in non-informative? Why is this trivial and so on? See, this is non-informative because it tells me that there is a lower bound. But I don't want the lower bound, right? So in a worst case, I can end up getting infinity. Infinity will also satisfy this inequality, right? Yes or no? So that's why I'm saying this is not an informative lower bound. So, but if I have a lower bound like this or an upper bound, so an upper bound like this, you see that if gamma goes to 0, they're equal almost. Correct? So this is equality holds as gamma goes to 0, gamma goes to 1, not useful. Because this goes to again blows up to infinity. Correct? So if you discount high, you put high discount factor where only the short term actions are being considered, then what happens is you can really put a bound on this and say that this is how much I can reach close to the original solution. That's what we'll try to prove. Any questions? And this is an informative bound, and that's what we'll try to prove. And in trying to prove that, we'll be using a theorem called the Banach's fixed point theorem. The Banach's fixed point theorem is something like this. Let's have an intuition for the fixed point theorem first. So we have sort of used this before to say that something is a contraction and so on. So Banach's fixed point theorem says that an operator C is a contraction with respect to a norm if this happens. So don't lose me yet. So thing is, you have two vectors, say u and v, correct? And you pass it through this operator, right? Let's say C is the operator, script C is the operator, script C of u and the operator C of v. It says that so this is the initial distance between them, right? V minus u. Do you agree? Fine. Okay. And I say that this is C of v, C of u, and this is C of v. This is, do you agree, Cu minus Cv? Questions? So a contraction is defined like this: Cu minus Cv, the norm with respect to a norm is u minus v for some constant c. So what does it say? It says that as you keep on putting this operator, so if we keep on passing any vector through this operator c, this would only bring the vectors closer together. Always, every time you put it through the operator, it would only bring it closer together. So ending up, what will it end up? Intuition? There will be a collapse, right? If every point, if you keep on keep on decreasing the distance between every point, if you keep on doing this contraction operation, what will happen? You'll collapse to a fixed point, right? For every step, you're decreasing the size, the length between them. You want me to explain something? So here, all I'm trying to say is when you pass it through this operator, the contraction operator C, what happens is these vectors become closer to one another, right? The U is passed through C to get Cu, V is passed through C to get Cv. The distance between them, distance is lesser. Distance is lesser than V and U. Is this okay? Can represent this like this. This distance is larger than this distance. Okay. Any questions? I'm waiting. Okay, so if this happens every time, yeah,
How do we formally define a contraction operation?
that's what I said. So anytime you pass this contraction operator, say two vectors you pass to the contraction operator, this will bring the vectors closer. That is C of U minus C of V. The distance between C of U minus C of V is lesser than the distance between U and V. So look at the diagram and look at the definition here. Okay. This is the definition.
Okay.
And the diagram and definition make sense. They're fitting together.
Yes, yeah.
Okay. So every time you pass it through this operator, they're going to bring it closer and closer. Fine. That is okay. So now if that is done, so as you can clearly see that 2 points would always keep going closer to one another and they would collapse. So this Banach's fixed point theorem that we'll be using will not prove this theorem, but the intuition is very clear, is that if this happens, if C is a contraction, then there exists a unique fixed point such that C V pi is equal to V pi, because all we are seeing is it is going towards that. Because any vector, two vectors you're taking, they're coming close to each other. So they have to come close to a single point is what it says. That is V star. There exists a unique fixed point V star such that the contraction operator would return the fixed point to us back again. So, okay. So using this contraction or the using Banach's fixed point theorem, we have to show that the T operator that we define in reinforcement learning using Banach's fixed point theorem, show that the T operator is a contraction and has a unique optima, unique fixed point. Can you help me do that? Do you remember the T pi operator, T pi of V? What was it?
R plus P pi of Vs. And R
Yes,
plus
so
P pi into Vs.
correct. So we define Vs as R of S A S dash plus gamma times Vs dash given S is given S. Yes or no? This is how we defined it. And then since it was an expected value, we said that any contraction, any operator would be defined as R. If we take the expectation out, the A and S will go out, only what is given will remain, right? Plus gamma times C. So only what is given will remain. So P pi of S dash given S into V of S dash. That's all we will have. Yes or no? Do you agree? Fine, from S to S dash you're going and you will sum over all the S dashes for V pi. That's what I'm writing down, correct? The expected value. Right, this expected value is conditioned on P of S given S dash, and this is conditioned on only S. Okay, so we said that, so this in matrix form, we said that, go back and see the contraction operation once again, the T pi operator, the Bellman operator, T pi P. Okay, so this was our Bellman operator. We have to show that this operator is a contraction. How do I prove it? So this is our first theorem that we'll be proving. Help me. Any idea? So all I'll do is say take for take two starting points, v and v dash. So now what will I do? The operator, what will the operator do? Tv, t pi v minus t pi v dash. This is what we have to compute, yes or no? This is what we have to compute. This is, what will this be? Please interact. This is not difficult. Yes or no? I just put it.
P pi's are cancelling, but again, could you just like explain like I feel that I can't follow the theorem, fixed point theorem.
You mean all? Did you follow the operation? See, t is an operator, right? It will take your v to another vector. The operator will, as you only had said in our previous class, that it will take any vector and it will convert it into another vector.
The definition I understood, and now like I feel that I can't understand again. Like,
okay, so what I'm trying to say is t is an operator, right? Which will convert one vector to another. That's how it is defined. Yes. It converts one vector to another. So now I'm telling you, so that take any two vector in this vector space. This is the vector space. Take any two vector in the vector space. Use the same contraction operator on them. Okay, no problem. This is clear?
yes, that's clear.
Now what it says is, as you use these contraction operator on this two vectors, these two vectors will come closer to one another. You see this diagram D. See, uv had a distance between them. That is this distance, this white line that I am plotting. When I passed it through the contraction operator, they came closer to one another. Is that fine?
Yeah, that's fine.
Okay, then the fixed point theorem says that for any contraction operator, there exists a fixed point. That is because every time you're passing it through this contractor operator, it is coming closer to one another. Where else will it go? It has to go to a fixed point, right? For any vector in the space. That's what it says. That is V star. Okay.
Yeah.
So now what I'm doing is we know what is the Bellman operator, correct? Bellman operator is fine.
Yes.
So now the Bellman operator, I put the Bellman operator value and I take p pi, and this is the d norm that I'm trying to find with respect to d norm. Now you see, look at this thing. So if it is a d norm, do you see this equation somewhere? Have you seen this equation? Have you seen this equation somewhere? Anyone? We just derived it. Non-expansive. See? Where did it go? See, non-expansive. Yeah, there you go. Isn't it? For any p, multiply the probability matrix, the vector will always be smaller. Right? Do you see the non-expansive matrix? I'll put the red around it. Okay, so now clearly I saw that I have this p pi matrix over here. By non-expansiveness, I will get gamma times v minus v dash. Correct?
Yeah.
So this shows that there exists a t pi. So this is another proof. We have done a proof extensively last time, but this is another proof of saying that t pi equal to v pi exists. Since t pi is a contraction with respect to the d norm by Banach's fixed point theorem. This exists. So this is one thing I proved. Okay, very good. So t pi equal to v pi, we have proved again. Now, the second thing I want to prove is using this operator. Now, recall what was our the motive of today's session. What was the second motive? Agenda.
To
The
find,
agenda. Okay.
yeah, the closeness of the 2 points. How
Good.
how far they.
Good. So let us try and find how close these points are. These points phi w hash and w star r. Okay, so let us try and find that. Okay, let's try to find it. So how will we find it? First, let us try and find the phi w hash. What is w hash? Do you recall? This is also a linear regression problem. So people who are doing AI can also keep this in mind. This will be the same equation. Phi inverse phi
Transpose of
d v pi. Correct? This was our equation. Correct. So if I write phi
yes.
of w hash, I can write this. So now I will define something. So see, this is, as you recall, do you remember the geometry of this? So look at this geometry. So this is basically what? It is basically projecting onto the column space. This is the column space. Column space of phi. So I'm projecting out in the column space of phi using a projection matrix P, correct? Let us say this is the projection matrix gamma. Projection matrix. So I'll show you what is this projection matrix mean. So if this was your V pi, this can be written as a projection matrix V times. This is what I taught last time in my course as well. I think, yeah, where we take any vector, you can project it onto the plane and you can write it in terms of a projection matrix into the vector. Correct? See, all you are doing is you take this vector, you project it.
Yes.
And the projection is being done by this projection matrix. So let's try to find out what is the projection matrix over here. Yeah. So see, the projection matrix is this. Do you agree? This is G for us. I'm not using P. Normally in linear algebra, you use P, but you have a lot of P's over here, probabilities and so on. So this is G V pi. Do you agree?
Yes.
Okay. So the projection matrix has been defined. So now after defining this projection matrix, okay, I have defined the projection matrix. We have to prove that the projection matrix is non-expansive. Okay. Prove non-expansive expansive projection matrix. Okay, let's do that as well. Not a big thing to do. Okay, so now you see, so what was the agenda? So what is non-expansive again? Do you remember? We have to show that this vector v is greater than gv. Yes or no? This is what we have to show by non-expansive.
Yeah.
Now tell me, how do I show this? This is a very, very common way of showing things. You prove a lot of theorems in linear algebra by doing this trick. So I'll start from v pi. Yeah, tell me.
So somewhere down the line, we would be using Cauchy-Schwarzer because the idea is clear that the projection is a cos theta component, and we have to just show that it's less than the length. So
yes, you will be using a very similar idea as Cauchy-Schwarz inequality and show that cos theta is 0. We are 90 degree here. That is theta is 90 degree. Let us see. So you can, whenever you do Cauchy-Schwarz, you can do something like this. I can add and subtract gv pi. That's what I have to bring, right? I have v pi with the norm of v. I want to bring this g norm, whatever I have, right? So let's try add and subtract this. So if I add and subtract this, I will have v minus gv. And if I put a square also, plus gv squared. This is what I wanted to bring. See, I have brought that term over here. I know this term is greater than 0. I have one extra term remaining. So let us look at that term. Tell me the term. 2 times v minus gamma v transpose, or we can even put the other one first. V transpose gamma transpose v minus GV. Is this fine with everyone? Is this correct, or do you think there's some mistake over here? So if you are not following, I will write it down for you again. Okay. Transpose D V minus GV plus GV. Is this fine? This is correct? No problem? Clear? This is how we define the D norm. Now, one term is this, one term is this. Correct? So the 2AB term will have a D in it. That's how it is different. Okay? Is this expansion clear? Just do the algebra from this step to this step. It will, yeah. So now let us try and write this V transpose G transpose D. So let us look at this term, term 1. Look at this term, term 1 is equal to V transpose G D V minus V transpose G transpose D GV. So I will look at this term now and I'll see how is it, as Orthodox was telling me, if we can prove that this dot product is 0 or not. That's what we'll try to prove. Okay, let's try and prove that. V transpose, again G transpose, can you tell me what is G transpose? Even if you're not following, let's look at G transpose only. Just look at this matrix, G transpose GD. What is G transpose? What is the matrix G? Phi. Recall. We defined it just now, no? This term, this matrix, phi of phi transpose D inverse phi transpose D. Correct? Okay. Yeah. See, phi transpose D. Transpose D phi of phi transpose D phi inverse phi transpose D. Okay, with everybody? What can this be written as? Can you help me? D transpose phi transpose D phi inverse phi transpose D. So this D is here. This term is this term. Phi transpose D phi inverse phi transpose D. Now anyone can you help me? What can I do this? Can I do with this? Are you following?
As I can see there, there's a phi transpose d phi and a phi transpose d phi inverse, and we are just gonna
Correct. Remove them, as you are rightly saying. Very good.
and we get same thing again.
Correct. So what do we get? Just see what we got. So this term that I have over here, or rather this term that I have over here, right? This term is what?
This term is again
Sorry, this one. See, this term is this term that I had over here. I got it from G transpose. Yes or no? See, G transpose is this. See, this is G transpose. Yes or no?
Yes, it says G transpose D.
Correct. Or D transpose G, whatever you want to write. Both are the same. So this can be written as V transpose G transpose dV minus V transpose G transpose. So this term became G transpose D, and this becomes 0. Yes or no? Therefore, clearly what we see is V or GV correct, is perpendicular to V minus GV in the D norm space. The D vector is critical here to make them perpendicular. Okay. With respect to this diagonal matrix. Okay. So now what did I end up proving? So this term goes to 0. Goes to 0. So what do I have now? Tell me. VD squared is equal to GV squared plus what else? V minus GV. Yes or no? Squared. Any questions? So now how do I prove non-expansiveness from this? This is greater than 0, which means this is, tell me which side is larger. Clear? Any questions? So we prove non-expansive property. Okay. So now the second property that I'll prove is lemma 2.2, right? Yeah, 2.2 is that G T pi is a gamma contraction with respect to the norm D. So that is, these are all, do you see that I am trying to bring it down to the same question? See, T pi equal to V pi, I know already from the in my tabular form. Now I'm trying to find out the same form in the TD0 algorithm, because I don't have this TD0 algorithm. I don't have access to the VPIs. I don't have access to the model, and I only have an algorithm that I define. So I'm trying to find out what is the operator, what is the contraction, and what is the fixed point. Fixed point we have found, and now we are trying to see how different are the fixed points from one another. Okay, so now we are told to find that G T pi is a gamma contraction with respect to the D norm. Now tell me, how will I do this? Any ideas? What is, first of all, tell me G T pi of a vector V? Tell me first operator, use the operator R plus gamma P pi V. Yes or no? This will give me a vector. Right? Now I can multiply the matrix G with this. What is G? Phi transpose D phi inverse phi D.
Phi transpose D.
Yeah, phi transpose D. So now, okay, I forgot to mention one thing. I was sorry for that. So whenever I took phi transpose Y somewhere, right? I took this, and this is not equal to 0. So I always assume full column rank. Okay. So full column rank, if it exists, there's no null space. That's what I'm trying to say. If Y not equal to 0. So that's what I'm trying to say. Always not equal to 0 means that there's no null space. Therefore, I am going to assume that it's a full column rank. That's why these are all falling into place. Otherwise, they will not fall in. These equations won't hold. That I'm assuming that there are enough states for, so there are 5 dimensions in the vector space or the features. There I am assuming there are thousands of states or examples that I have in the data. So there's not going to be a problem of full column rank not existing. Okay, so that was one detour that I wanted to convey. So okay, so now this is your G pi of this. Okay, fine. So now let us try to see if it is a contraction or not. Can you help me? How do I see that? What do I do? Assume, consider. What should I do? People who, all of you who have been following, how do I prove it is a contraction? What do I have to consider first? V and V dash as 2 vectors. Then what do I do? G T pi of V minus G T pi of V dash. Okay, that's what I have to find.
Yeah, I have to find an upper bound for this.
Correct. So
I have
let's
to
see. Help me. How do I do that? First, let me put T pi inside. Is this fine with all of you? G is a matrix, so I can take G common. Okay, this is a vector. Vector, vector. And G is a matrix. I just took G common. Now what will I do? Again, I proved the lemma.
now I now I can just use the last result I got.
Yeah,
I can say that it's less than equal to gamma VV
very good, very good. Lemma
V V
2.1.
dash.
Correct. So gamma from lemma 2.1 by non-expansiveness. Non-expansive. I can say that this is less than T pi V minus T pi V dash D. So now I already have proved something. Do you remember this? Lemma 1.
Yeah, less. This is equal going to be equal to less than equal to. Uh, that's what I wanted to say. This gamma.
Yes. So just see this. We have already proved this in lemma 1 that T pi is a Bellman operator is a contraction. So now we have shown successfully that G T pi is a contraction. Very good. So as soon as I show G T pi is a contraction, what do I know? Banach's fixed point theorem. Gamma A is between 0 and 1. Fixed point theorem. Tell me, what will I immediately know? The immediate observation is that there exists a V star such that G T pi V star is equal to V star. Do you agree? It's the unique fixed point theorem. Okay, any questions? So now the quest is to find that fixed point. If we find out one fixed point, we know that is the fixed point by Banach's fixed point theorem. Okay, so now we'll go to the final lemma of today's session. That is, we will show that phi W star is the fixed point of GT pi. How do I show that is the question. So I will say this is lemma 3.1. Lemma 3.1. I will show that phi W star is the fixed point of GT pi. How do I show that? Let's try to find out. So first, let me tell you again, what is G star? W star, sorry. Remember, recall, what is W star? A inverse B, which is phi transpose, or am I writing it correctly? Phi D phi.
You were writing correctly.
Okay. So A
No, no,
was,
no, no. I mean, phi transpose is correct.
okay, phi transpose D phi I
Okay.
minus,
Yes.
this was our A,
Yes. This was our
inverse phi dr. This was our B. This is
yes.
our A inverse, or the other A, because I'm putting it correct. So now instantly I can do one trick. What is the trick? I can take
I can
the,
do the inverse and I can cancel out phi transpose.
very good. So all I'll do is I'll put this, take this inverse and I'll write this in this form. Phi d 1 minus gamma p pi phi W star is equal to phi transpose dr. Okay, which is equal to phi transpose d phi w star minus phi transpose d gamma times phi transpose d p pi phi w star is equal to phi transpose dr. Very good. So I can write this as phi transpose d phi w star is equal to, as you were telling me, phi transpose d I will take common, and I will write this as reward plus, so phi transpose d I took common, p pi phi of. Does this ring a bell again? Can I do something more with this? See, this is simple. So what I'll do is I will take w star is equal to and take the inverse of this. Phi transpose d phi inverse phi transpose d r plus. I'll give a very similar problem for your assignment where you'll be considered two-step reward and you will try to prove the same step list of steps. That will be around 20 to 30% of the course. So we've done that so extensively, like 20% maybe. So now I'll put a phi here and I'll put a phi here. So now do you recall, do you see a similarity, some equation somewhere? What is this? Just check. We just defined it. G is this, yes or no? That is G. So this is G R plus P pi pi W star. Now is this very familiar? Do you
Yeah,
find
this
this?
is, yeah, G of T pi of phi W star is equal to phi W star. So we have essentially proved that phi W star is the fixed mount.
Good. Therefore, phi W star is the fixed point of G T pi. So now why did I take all this hassle? Is the final cherry on the cake. Is trying to prove this equation. Let me just copy this final cherry on the cake. Okay. Yeah. This is the final lemma or the final theorem that I wanted to prove. This is the theorem, convergence theorem, the deviation in convergence. Okay, let's try and do that. So, okay, where do I start from? The starting point would be, see, what do I want first of all? I want this. Do you agree? I want how far is the converged point from the actual value, right? So you recall this. So this was your V pi. Again, I'm drawing the geometry. Say this was your phi W hash. We have obtained some phi W star. I want to say, okay, let us say this is phi W hash. Say this D1 and D2. What is the distance between D1 and D2? How far? That is how far D2 is from D1. That's C times something, D2. Okay, so I'm trying to see how large. Let me just write it down. How large is the distance? So, okay, let us try to find that. Simple. Phi dash. What should be the first step? Again, if I have this equation, what can I do? So I need hash to come in from somewhere. So first step should be bring in that hash term. I can do that. W star, W hash, and subtract W hash. And V pi also you subtract. Next, what do I do? Can you tell me what do I do? See, one term yeah.
Cauchy-Schwarz.
I don't think you need Cauchy-Schwarz. Triangle inequality will do. No, I want this term, right? See, this term, if I need to, correct. So if I use triangle inequality, I can write this as phi of W hash minus this D plus Q phi W star minus W hash. Is this fine? Okay, so we have got the equation that I wanted. Two sides I have got. I just want to play with this term and try to express this term in either of these terms. Let's try and do that. So how do I do that? Let us consider this phi of W star minus phi of W hash D. We have just now proved one theorem. Can you tell me what the theorem was? We have showed that this is a fixed point. Can I write this as G T pi of V pi, or rather, sorry, phi W hash, W star. Phi W star is a fixed point of GT pi, yes or no? Therefore, GT pi phi W star is equal to phi W star, yes or no? So I just put it this here. And the second part, what can I write? Can you tell me? We have also defined something like this, right? GW hash is GV pi. Do you remember? This is the projection operator.
Right.
So we define this here. Just recall. Yeah. So see, definition of projection. GV pi is equal to phi W hash. So that's all. I'll just replace it with G V pi of D. Next, what do I do? Question. I can take something common here. What? G common. T pi phi W star minus V pi. Next, what can I use? See, everything is falling into place again. Which lemma will I use? Lemma 2.1. What is that lemma? G is non-expansive, yes or no?
Yes, less than equal to T pi W star minus V.
Minus V pi. Good. Now again, I know another property. What is that property? I know by Banach's fixed point theorem that V pi is equal to T pi V pi. Yes or no? Okay. So this I can write as T pi phi W star minus T pi V pi. Again, I can take T pi common as the operator. It's a linear operator. I don't even need to do that, sorry. So now T pi is a contraction, yes or no? Do you agree? T pi is a gamma contraction.
Yes.
I can write this as great. So I have written down this term. So I'll just put it over here. So where is the equation? The dagger equation. I'll just write it down over here. Phi W star minus V pi of D is less than phi W hash minus V pi of D plus, see, this is again an inequality. I can write this from dagger and double star. I can write this as Okay. Hence I get W star minus V pi of D is less than 1 minus gamma V phi hash minus T pi. Okay. So it says that, see, this was the optimal point. So if this was your optimal point, it says that your algorithm can increase this optimal point by a factor of 1 by 1 minus gamma, and then end up reaching that. So this is opt, and your algorithm can range anywhere here, TD0 with lean function approximation. Okay, that concludes TD0 algorithm with linear function approximation. So from next day, we'll see off policy TD0 and then Q learning using linear function approximation, and then slowly move into policy gradients. So if there are any questions you want to ask regarding today's session.
I think that we should go back and do the proof ourselves because this was so involved and there are some gaps, and we should get back to you after we cover this.
Okay.
I mean,
See,
the main points were clear. Obviously, the main ideas were clear, but because
Correct.
I think we need to connect it in our minds of how
Correct.
sequence.
You need. So that's why I'll give you a question that will be exactly this question, but it will be with a little involved. That will be, we did it for one step reward function, right? So we took one step and calculated the reward and then used the value function. Correct? Yes or no? That's what we did.
Yes.
So I will tell you to do the same steps up to this using 2 steps of reward function. That is, one step you take, go to the next step, and then you take the second step. That will be your assignment question. Only that will be the assignment question from TD0. Rest will be all implementation. Okay. Yeah, you're absolutely right. Then you'll absolutely have this entire thing crystal clear in your mind. Okay. So then I'll stop recording.